Last chapter we learned all about acids and bases and how to measure the pH, which is an indication or a measure of the acid strength, or in particular it's the hydronium ion concentration. Now this concentration, or the pH, can affect physiological processes in the human body or in any life, as well as chemical processes. So it is important that the pH is at the right strength for certain processes to occur efficiently, and sometimes life and death can even depend on having a pH balance. And so one of these examples is, of course, our blood. Our blood has a very effective so-called buffer system, and that's what this chapter is about. What is a buffer? How do we maintain the pH? Because we already know that a little bit of acid, especially strong or base, can affect the pH drastically. And so our body does an extremely good job maintaining the pH at about 7.4. And so it has buffers. And why is that important? Well, a little bit of acid can, for example, knock the oxygen off of the hemoglobin, right? So we already have seen the hemoglobin, of course. HB doesn't do it justice. It's a much larger protein. But the point of it is that it carries oxygen from the lungs to the muscles or the cells or wherever oxygen is needed, and it only releases that oxygen where it is needed. Now, what happens if our blood pH is too low, so that's indicated here by H+, it'll shift that equilibrium, it'll attach to the hemoglobin and knock the oxygen off, and then that can have some catastrophic effects. Okay, and so there are substances in the blood that will prevent that from happening. There are substances that will actually react with H+ and take it out so that it doesn't react with the HB, with the hemoglobin, and the same is true for hydroxide if you had any source of hydroxide. A couple of examples where this can be an issue. For example, ethylene glycol, which is antifreeze. It can, if it gets into your bloodstream, we have an enzyme called alcohol dehydrogenase. It can turn that into glycolic acid, which is what this is here. You already know that this is an acid. So this enzyme converts an alcohol, that's a functional group, into an acid. Okay, and so it will also do that for ethanol, which is the alcohol that we consume. But it turns it into acid aldehyde, so that doesn't make our blood acidic. You also might have heard of methanol poisoning. So methanol will also interact or be consumed by the alcohol dehydrogenase, an enzyme in our body, into formaldehyde. Now, formaldehyde can do some damage to us, and so that's not a good thing. The ethanol we can handle. Sometimes the second alcohol here of ethylene glycol can also be converted to make another carboxylic acid on the other side, and that's oxalic acid. But either way, what this does, it's a weak acid, just like vinegar, any of those acids that we've seen that have that carboxylic acid, gives off a little bit of H+. And if that's in our blood, as I said, it will knock off the oxygen, and then so hundreds of pets actually die from that because it tastes sweet, like the ethylene glycol and antifreeze, if it leaks from a car and the pets lick it up. And so what we actually do is we give a 10%, not we, but doctors, people that know what they're doing. You know, my doctorate degree isn't really a real doctorate degree, so I'm a fake doctor. So they give a 10% ethanol solution as an antidote, right? So what that will do is the enzyme here will then compete to either react with the ethanol or with the ethylene glycol, and so the goal is for that ethylene glycol to just be going through the body without producing acid. And so the same thing is actually given to people who consume methanol. They are given alcohol, or the ethyl alcohol, which is the one that's part of the fermentation of sugars. Okay. So how does it work, right? How does a buffer work? What is in our blood that mops up acid, reacts with acids and bases to maintain the pH balance? So as an example, I'm going to use carbonic acid, which, if you remember, if we have carbon dioxide, and we pressurize water with it, we get carbonic acid, and then that gives off the bubbles, the gas that makes the effervescence of your carbonated beverages. But carbonic acid will also, of course, react with water to form a conjugate base and the conjugate acid, right? So it will make your solution, your water solution, acidic because it produces hydronium ion. But we also have the conjugate base, and we know that the conjugate base will also react with water to form the acid back, right? So in this case, I have it actually reacting with an acid. What we've seen before from chapter 16 is it reacting with water to form, and that's a beautiful, beautiful arrow here, double arrow. Okay, to form the acid and then some hydroxide. That's why it's called a base. It will act as a base, form some more carbonic acid, and in return produce hydroxide. So we do know that it can react, that the conjugate base can react with an acid to form to mop up some of that H+ and not affect the pH so much. So if you have a mixture of both the acid, the weak acid, and its conjugate base, that's how you create a buffer. You can actually add a source of conjugate base in the form from a salt, right? We already know that if we have sodium hydrogen carbonate, that it will connect as it'll produce this ion in solution. So we can add some of that to the acid to increase the buffer. It can also react with hydroxide, of course, if we have a system which contains the conjugate base and a weak acid, a mixture of both. So then the base will react with the acid to shift this equilibrium to the right to form a hydrogen carbonate and water. So you can have a little bit of a buffer system by taking a weak acid and a source of its conjugate base. So the example given here is acetic acid. Acetic acid actually dissociates into H+ and then acetate. And so the conjugate base is acetate, and if you have a source of acetate such as sodium acetate, you can create a buffer, right? So you just have to mix the two, and then we can test its buffer capacity and see how that resists the change. Now if we have solutions of just the acid here, the same concentration of the conjugate base, just the conjugate base, and then a mixture of the two. So we have 0.100 molar solution of just the acid, which obviously would give us a pH that's lower than 7 here. This has a pH of 2.9. If we don't have any of the weak acid and just use the conjugate base, here the source, we already did some ice tables where we set up this reaction here. We know this in solution will break apart completely 100% and produce 0.100 moles per liter, if this was in a liter, for example, of the acetate ion, which will then react with water in an equilibrium reaction to form acetic acid, and then it's not gonna fit, but it's going to produce some hydroxide, and that hydroxide is causing the pH of this solution to go up past 7, because we know this is a base, and there is that relationship. Remember, we can calculate the Kb for that. As long as we're provided with the Ka, there is a relationship. The relationship, just as a reminder, Kw equals Ka times Kb, and if Kw is 1.00 times 10 to the minus 14 at 25 degrees Celsius. And so then if we have a 0.1 molar solution of the mixture, which is we take 0.1 moles of the acetic acid and 0.1 moles of sodium acetate, and then we mix the two together and add enough water to make a liter, so we have a 1 molar solution, we would actually have a pH that's somewhat in the middle. Okay, so let's see what happens when if we can calculate that pH with an ice table. If we had a mixture of 0.100 m acetic acid and 0.10 m sodium acetate, and so it's important that we have this in 1 liter. We can set up an ice table, and so this is now a little bit different. Initially, we know we have 0.100, and since we have a liter, it doesn't matter if we have moles or molarity, and we initially have none of that, but we do have some of the conjugate base, right? So here is the source of that, and it's exactly 0.1 moles. So we have 0.100 m. So that's, I'll leave that off. That's the difference between what we've done before. So we already have some of the product, but we don't have any of the hydronium ion. Well, we do have some from the autoionization, but it's essentially 0, so we can assume that it's going to shift to the right. So we're going to go minus x, plus x, and plus x, and at equilibrium it's 0.100 minus x, and this is x, and this is 0.100 plus x. I also have to give you the Ka here. The Ka is 1.8 times 10 to the minus 5. Now if I plug that into our equilibrium expression, 1.8 times 10 to the minus 5 equals x times 0.100 plus x here, right? The products over reactants divided by 0.100 minus x. We can make the assumption, because this is a weak acid, we have an equilibrium constant that is rather small, plus we have some product already, which will push that equilibrium even more to the left as it dissociates and produces H+, right? So that means that we can make an assumption that x is very, very small, and so that turns our equation into x times 0.100 divided by 0.100, and so in this case it's convenient. The math actually is very easy. The Ka is going to be equal to the pKa, or in this case x, the hydronium ion concentration, is equal to the Ka, and so if we take the negative log of 1.8 times 10 to the minus 5, that would be the pH, because this is equal now to the hydronium ion concentration at equilibrium, right? And so the pH would be 4.74, which is the same thing as the pKa, because the pKa is simply the negative log of the Ka, so which is 4.74. Alright, so I have this clean here. Remember that if you are given a salt which contains the conjugate base, this will break apart completely. There's no equilibrium here, so we get a 100% dissociation. The sodium ions that are produced are just counter ions. They don't have any effect. They're not part of this equilibrium. But so we already have initially, before this shifts to the right, we already have 0.1 molar solution of the conjugate base. This is, again, that's our initial concentration before it splits, so we know we have 0.100, but it is going to go to the right by a factor of x. And so we have minus x plus x plus x. And then we solve the algebra, which is actually really, really easy. And if you wanted to do the test, you take that Ka and you divide it by the initial concentration times 100, and you get a dissociation of 0.018%, which is to be expected for a couple of reasons. First of all, it's a weak acid, but also we do already have some of the product present here from this equilibrium, right? So we have Just to make sure here, the A minus here is the acetate. So it's product over reactants. So this would be the concentration of C2H3O minus times H plus divided by the acid, which is H, C2H3O2. It's just much easier to have a general equilibrium constant where all of the weak bases, acids, are going to look like this, where this A minus is the conjugate base of the weak acid and HA is the weak acid. Okay? So you can also, you don't have to do an ice table, you can actually use the Henderson-Hasselbalch equation, which is the pH equals the pKa plus the log of the conjugate base, the conjugate acid ratio, which in our case is 1 to 1, right? It's 0.1 divided by 0.1, so the log of 1 equals 0, and this is how we know that if the concentrations of the acid and the base are equal, we have a pH that's equal to the pKa, and we calculated that already. So this equation is really much easier to use. And so this is just a nice little introduction to the material. When we come back, we're gonna see what happens when we add an acid and a base to a solution like that.